know that if we're integrating e to the x, so if we took the derivative of e to the x, we got itself, right? So if we integrate e to the x, then we get itself. Okay, so the integral of e to the x is e to the x plus c. But it's not the same for like e to the 5x, e to the 7x, just like with the chain rule. When we integrate something like that, we're going to have to kind of think about the U-substitution, okay? Eventually, I think you guys will be good at doing this without a U-substitution, but let's see it for now. Okay, so if I have u is equal to negative 2x, then du should be negative 2 dx. So I'm going to have negative 1/2 du is going to replace the dx. So my e to the negative 2x is going to become e to the u. I'm just letting the u be negative 2x, not the e to the negative 2x. So then I have e to the u, and then I'm going to have times my negative 1/2 du. So that negative 1/2 can kind of go to the front. We can ignore it. When I integrate e to the u, though, I do get itself. I get e to the u. So it's going to be e to the u plus c. Now, I don't want to do a plus c, though, because I have numbers. So if you remember when we did u substitutions, what we did is we changed those x values from before. So our numbers 0 to 4. We changed those into u values.
So does it end up being like e to the u times u?
Hang on. So if I have u of 4, so I plug in 4 into my negative 2x equation right here. What do I get? Negative 8. And u of 0 is 0. So I'm going from 0 to negative 8, which some of you guys might not like. You might want to switch it and say negative 8 to 0, and then you make the whole thing the opposite. Doesn't matter. You can keep it the way it is, or you can switch it. So now when I integrate e to the u, I get itself. So I'm going to have e to the u, 0 to negative 8, negative 1/2.
So it would be like e to the u times u.
No. The du just goes with the integration sign.
If you had like e to the 5x, you would do like e to the 5x plus 5.
But not 5x, right? Easy. All right, so now I'm going to plug in the negative 8. So I have negative 1/2, and then I'm going to have e to the negative 8 minus e to the 0. So I get negative 1/2 times 1 over e to the 8th minus e to the 0 is 1. So if I was simplifying this all the way, you could multiply the negative 1/2 in, or you can, the way the AP test would probably simplify it is it would do like over 2. But since we have that negative, well, I don't know how they would simplify this because you do have the e to the negative 8, don't you? So maybe it's like negative 1 over 2 e to the 8th plus 1/2. So they'd probably write it like 1/2 minus 1 over 2 e to the 8th. Or they might get fancy and get common denominators. So multiply the first one by e to the 8th over e to the 8th. So they might also write it as e to the 8th minus 1 all over 2 e to the 8th. See what I'm saying? Like get common denominators here. So they might do that as well. Okay, so the next one.
Wait, what, do we need to find the actual number? Is it definite?
That is a number, right? E's are numbers. I prefer the numbers with pi's and e's and those numbers in those. Those are the exact numbers, right? Finding a decimal approximation is not exact. All right, so the next one, we would let our u be 4 plus e to the x. So du then is e to the x dx, which is replacing this e to the x dx for us. Okay, so we're going to have u to the 5th du. So we get 1/5, not 1/5, 1/6 u to the 6th plus c. So it's going to be 1/6 times 4 plus e to the x raised to the 6th plus c. That's our answer. All right, so same idea. We're just doing our chain rule. So this next one, what do you guys think our chain is? Or not our chain, our u. Square root of x. So we're just getting rid of the chain rule somehow. So our du then, remember this was x to the 1/2, so it's going to be 1/2 x to the negative 1/2, which is really like 1 over 2 root x is how we usually see it. So that's almost what we want to replace because we have our root x, our 1 over root x dx. But we have that extra 2, right? Yeah, so you can kind of multiply that 2 to the other side if you want to, so then we have our 1 over root x dx like we want. So we're going to have 2, and then the integral of e to the u du. So it's going to be 2 e to the u plus c, which is 2 e to the square root of x plus c. So your u is usually the exponent for these ones. So like for the next one, I would let it be sine of x. So that way I'm going to end up with an e to the u. So if I have u is equal to sine of x, then du is equal to cosine of x dx. So when I'm integrating, I do have my e to the u du, which ends up being e to the u plus c. So it's e to the sine x plus c. Okay, so some of you guys are going to be good at doing some that look like they need the u substitution, but they don't really. Like something like I'm going to put a number 5 in here. What if I had e to the 7x dx? So this is kind of what Katie was asking about. She's like, I know when I take the derivative of e to the 7x, I get e to the 7x times 7. So what do you think the integral is? 1/7 e to the 7x, right? Do you see where that comes from? Because if I did do a u substitution, I would get du is equal to 7 dx. So I'd have 1/7 du equals dx. So I'd replace, and I'd have a 1/7 that I gained, and then e to the u du. So when I integrate, I get 1/7 e to the 7x plus c, right? 1/7 e to the u plus c. So 1/7 e to the 7x plus c. Okay, do you guys see it? So if I had like e to the 1/2 x dx, what would my answer be? I'd have my e to the 1/2 x, but I'd have times 2 instead of the 1/2, right? I need to get rid of my 1/2 with the derivative, from the derivative. So I have a 2 e to the 1/2 x plus c, right? So some of those easier ones you can do pretty quickly. But if it does have something like sine of x, cosine of x, it's always good to like write out the u substitution. Sometimes you forget negatives and things when you try to do it in a hurry. All right, so we've done these before where we find the particular solution, right? So this is when we are finding the c value for a certain differential equation, and we're writing our final f of x function. So I have f double prime equals 1/2 e to the x plus e to the negative x. So that means I have 1/2 e to the x plus 1/2 e to the negative x for my f double prime, second derivative. So when I find my first derivative, I'm going to integrate. So I'm going to have 1/2 e to the x. What do you think I'm going to get when I integrate 1/2 e to the negative x?
Negative 1/2 e to the negative x.
Negative 1/2 e to the negative x. Do you guys see that? Because I would let u equal negative x. I'd gain a negative 1. Right.
Oh, wait. I thought that said f prime up there, and I was like, how are you getting that?
The first one was f double prime. Okay, so we add a c, so do plus c. So now we look through here and we're like, well, I know that f prime of 0 equals 0, so I'm going to plug in 0. So be careful, it doesn't just go away, right? Because these are e to the zeros. So I have 1/2 of 1, right? E to the 0 is 1, minus 1/2 of 1. So I get 1/2 minus 1/2. So it does actually go to 0, but so c is equal to 0. But be careful, it doesn't always happen, right? Just like some people, when they see like things like cosine of 0, they're like, oh, it's going to be 0. No, cosine of 0 is 1, so you have to be careful with things like that. All right, and then let's plug in the next one, or let's find the next antiderivative. So f of x. So now I'm going to do the antiderivative of f prime of x was 1/2 e to the x minus 1/2 e to the negative x plus 0, right? That was our c. So you can just leave that part off.
Plus 1/2 e to the x.
So I get 1/2 e to the x, and then I get plus another 1/2 e to the negative x. It goes back to what f double prime is.
So those two just sort of alternate.
Mm-hmm. We call it an iterative function. It iterates, repeats. We do. So we're going to do, like, instead of doing a plus c, we can do a plus d. And we see what happens. So when I plug in my f of 0, I should get 1. That's what it's saying. So I have 1/2 e to the 0 plus 1/2 e to the negative 0 plus d. Well, that was lucky. 1 plus d is equal to 1. So d is also equal to 0.
Wait, why are you doing plus d?
Because when we do the antiderivative, we need a constant, like a plus c. So instead of writing c again, I do d. Or you could do c1, c2, c3. All right, so I get 1/2 e to the x plus 1/2 e to the negative x. So it does indeed like iterate. It keeps, like every second derivative goes back to that. Second antiderivative, I guess. Yeah. All right, so the next thing. So we've talked about this before. I've kind of previewed this and said, oh, you guys understand that like when you integrate 1 over x, you get natural log of x, right? But the way that we write it is always natural log of the absolute value of x. So if you leave off the absolute values on the AP test, you will be in big trouble. You got to do it. So natural log of the absolute value of x plus c. So it says, why do we need the absolute value? So if I tried to find the integral of 1 over x, we know what 1 over x looks like, right? It looks like this. So if I try to find that area, or that integral, I guess, from -3 to -2, you get that. So if I have the integral of 1 over x dx from -3 to -2, then I get the natural log of the absolute value of x going from -3 to -2. And if I had left those off, the absolute value, then I'd have natural log of -2 minus natural log of -3.
And you can't have a natural log of a negative.
Exactly. But we know that that's some kind of, like, that's a number, right? The integral is forming a negative result of that area, right? I should get a negative number. So that's why I need those absolute values, otherwise we can't do it. So it's natural log of 2 minus natural log of 3, which we could even write as natural log of 2/3, right?
How'd you get absolute value from like?
So that's what I was saying. You have to have the absolute value in your formula. Otherwise, it doesn't work. Because we can't do the natural log of -2. It's undefined. Okay? All right, so it says evaluate the following indefinite and definite integrals. So this first one, a little tricky. Any guesses on, it is a U-substitution. What should we let our U be? X squared plus 1. It's never just x. Okay, so we're going to let u be x squared plus 1. Now look, when we do du, it's good because we're getting that x dx somewhere. So my 1/2 du is x dx. So that's this part and this part. And then the x squared plus 1 was our u, right? So when we do this, we get the integral of 1 over u du, and we gain that 1/2 from our derivative, right? 1/2 du replace the x dx. So when I integrate 1 over u, and you can even think about it, if you have -1 and you're adding 1 to the power, that's like weird, right? So if you tried the power rule and you're like, oh, I'm going to add 1 to the power, I'm going to do 1 over the new power, right? That doesn't make any sense. 1 over 0, u to the 0, right? So that's why it's the natural log one. That kind of is a red flag, like, wait a second, this one has a special rule. So I get 1/2 natural log of the absolute value of u plus c. So it's going to be 1/2 natural log of the absolute value of x squared plus 1 plus c. Now on the AP test, if you wrote it like this, I told you if you left off your absolute values, you'd be in big trouble. But in this case, if you wrote it like that, it would be totally fine. So explain to me why it is totally fine. Yeah, Charles? It's kind of an even, not quite. It's positive, yeah. So because you have that x squared, is that what you're saying? Because you have x squared, it's going to, whatever negative number you put in there, it's going to end up being positive. All right? Well, what if I wrote it like this? Is that also acceptable?
Yes.
Yes, why, Olivia?
You have the half of that.
Because you take that 1/2 and you bring it up as a power, exactly. So there are lots of different ways that the AP test will write natural log functions, and that is the hardest thing for my students every single year. They're like, well, I don't see my answer. I'm like, it's there. It's just in a different form. So natural log and E answers can be disastrous to find sometimes. It's not very fun. All right, so this next one. So do I need a U-substitution? What do you think? If I do a U-substitution, what's U? r cubed, but then does that really like give us the 4 plus r squared? Not really. Is there something else we could do? So let's bring this r cubed into both pieces. So let's not do a u substitution. So we're going to have 4 over r cubed, which is 4r to the negative 3. And we have r squared over r cubed, which is going to be 1 over r. So you can leave it like that, or you can do r to the negative 1. I'm going to write it as 1 over r. And really what we're doing is we're breaking up this integral. We're just doing one piece at a time, really. I mean, you can do it all together. It's not a big deal. But this is how we do any like polynomial, really. Like when we integrate polynomials, don't we just do the rule for each individual thing and then add them all together? That's what we're doing. So the rule for the first part, if I have 4r to the negative 3, is I can use that power rule. I can add 1 to the power. So I have my r to the negative 2. Don't write r to the negative 4. A lot of people have been doing that. I'm going to have my 1 over my negative 2, and I'm going to multiply by that 4. And it's going to go from the 1 to 2. Well, what's the rule for the next one? How do I integrate 1 over r? Yeah, natural log. So natural log of the absolute value of r going from 1 to 2. So I have my negative 2 over r squared going from 1 to 2, and I have my natural log of the absolute value of r going from 1 to 2. So I get negative 2 over 4 minus negative 2 over 1, and then plus natural log of 2 minus natural log of 1.
Natural log of 1 is 0, right?
It is. So if you think about it, why is natural log of 1 0? Well, what if I had divided natural log of 2 over 1, right? Isn't that still just natural log of 2? Right, natural log of 1 is 0. You could use the division rule there too and just call it natural log of 2 over 1. All right, so I get negative 1/2 plus 2 plus natural log of 2. So my answer is 3 over 2 plus natural log of 2.
You do proof C.
Nope, because this was a definite integral. These were numbers, right?
Oh, right.
All right, so sine of x over cosine of x. So this is the integral of tangent, right? But we don't know how to integrate tangent. Is there anything on our derivatives drill where we took the derivative of it to get tangent? No. So now we're learning how to integrate tangent, actually. So if I have sine of x over cosine of x, it does involve a u substitution. Which one do you think is your u? Ah, no, it's the cosine of x. Usually denominators, things under square roots, right, the powers. So our du then is going to be negative sine of x dx. So you can kind of pull that negative to the front of the integral. So we're going to have 1 over u du. So we get a negative natural log of the absolute value of u plus c. Right, if I integrate 1 over u, I get natural log of absolute value of u. So I get negative natural log of cosine of x plus c. So some textbooks will write it like this. Some books will write it like this. How are those the same? Right, you can bring that negative 1 up as a power, and then it's cosine of x to the negative 1. So that's kind of weird. It's not arc cosine. Those aren't the same thing. That is not the same as 1 over cosine of x. Or, in this case, I'm writing it as cosine of x raised to the negative 1.
Even though it's notated with a negative 1, that doesn't.
It's not. They're not the same thing. It's just like f of x, or f inverse of x. You guys remember when we were in Algebra 2 and you learned f inverse? That's not the same as 1 over f of x, right? Those aren't the same. We just run out of symbols in math. We reuse symbols. It's very confusing. I don't know why. All right, so I know they
Draw a
should.
squiggly line, and that can be your new symbol.
That would be very annoying for a math teacher to type up. All right, so the antiderivative of tangent. So if I'm trying to take the derivative of something to get tangent out, it's actually the natural log of secant of x. That's how you get the derivative of tangent. Isn't that crazy? All right, a couple more. So if I have a to the x dx, so if I had something like the integral of 5 to the x dx, we know that if we were taking the derivative of 5 to the x, we get 5 to the x times natural log of 5. So what do you think the integral of 5 to the x is? Any guesses? Oh, I guess I gave it to you. It's there, isn't it? So it's 5 to the x over the natural log of 5 plus c. Because this natural log of 5, that's a number, right? It's all a number. So if I want to undo that number, right, undo the chain rule, then I divide that out on the antiderivative. So if you have your derivatives really good, then you can get your integrals really good. So this one, sorry, I'm going to finish this one example. It's going to be 3 to the x over natural log of 3. And we're going from 2 to 5. So it's going to be 3 to the 5th over natural log of 3 minus 3 to the 2nd over the natural log of 3.
Can you just leave it as like the
You could get fancy and you could like pull out a 3 squared, but 3 to the 5th is 243. So 243 minus 9,
234?
that's our answer. I would leave the natural log of 3 in there. All right, I just have this one last example, right? I'll do it really quickly, sorry. So this is a U-substitution. U is equal to 3x because we didn't have a rule for 2 to something other than x, right? So we want to write the 3x. So we get a 1/3 du equals dx. So as we're replacing, we're going to have our 2 to the u, and our dx is replaced with 1/3 in our du. How about our u of 2 and u of 1? So instead of going from 1 to 2 for x values, for my u values, I'm going to go from 3 to 6. There. So when I integrate, I'm going to have 2 to the u over the natural log of 2, going from 3 to 6.
Where'd you get the 4 from?
That's a u, sorry.
Oh.
So I have 2 to the 6th over natural log of 2 minus 2 to the 3 over natural log of 2.
56 over natural log of 2.
And then 1/3, 2. Is that what you're saying?
Oh, yes, it was probably in the 1/3.
So I would
56
probably write it
over
as
3 natural log of 2?
56 over 3 natural log of 2. But then think about other ways that the AP test could write that. So you could also have 56 over natural log of, what? 8. 2 cubed, right? So you could have that as well. So look for weird things. All right, you guys can go on your break.